Welcome to the Insightful Professor. With this video, we will conclude our brief introduction to PLSQL. We'll be focusing on a couple points. One will be expanding our discussion of embedded SQL to include cursors and cursor processing. With the second point, we'll address stored program units, stored procedures, and stored functions. We'll provide the basic syntax and the concepts associated with these program constructs. In earlier videos, we addressed most of the points listed here. We introduced embedded SQL in the form of a singleton select. This is a SQL select statement that retrieves exactly one row from the database. Often database I/O will involve processing a set of values one at a time. The singleton select is not suitable for this situation. In this video, we will discuss the use of a special work area called a cursor. While every SQL select uses a cursor, our current discussion will reveal how this work area is used and how to explicitly declare this work area, what is known as an explicit cursor. We'll define the steps required to work with an explicit cursor and then utilize the conditional and iterative processing features presented in earlier videos. Finally, we'll introduce stored procedures. A stored procedure is a PLSQL program that has been given a name, created as a database object, and can be invoked or called. The output of a query is a result set, a set of rows. A result set is processed using a cursor. Relational databases and SQL operate on a set of data, set-level processing, while traditional programming languages, including PLSQL, operate on only one record or one row at a time, record-level processing. This processing or behavior difference between the database and the programming language is referred to as an impedance mismatch. A cursor provides a way of dealing with the set-level processing and kind of bridges the gap between these two different approaches, set-level and record-level. A cursor is a work area through which the result of a set-level query is made available to the application one row at a time. When a program requires more than one row, a cursor can be used to work with the result set. In Oracle database, a cursor is a pointer to a private area that stores information about processing a specific query, a select statement, or DML statement. When executing SQL statements in a PL/SQL program, we have two basic options, an implicit cursor and an explicit cursor. A cursor is implicitly declared for all SQL data manipulation statements, and this includes queries that return only one row, the singleton select that we examined in our previous video. For the data manipulation statements, insert, update, delete, merge, the cursor is managed by the database system, which means as programmers, we do not have to write any instructions to control or manage the cursor processing. An implicit cursor does not allow instructions such as opening the cursor, closing the cursor, fetching from the cursor. However, an implicit cursor has attributes which allow us to access information about the cursor. An implicit cursor is closed after its associated statement runs. So the values of the attributes of an implicit cursor remain available to the program until another query or DML statement is run. Because of this behavior, there's only one implicit cursor available at any time in a program. The name given to that implicit cursor is SQL. The significance of this name is that it can be used to qualify references to the implicit cursor attributes that we referred to just a moment ago. Now, an explicit cursor is constructed and managed by the programmer. We'll write code and instructions for defining this and working with it. For a query that returns more than one row, the following options are available. A cursor can be explicitly declared and processed manually. We write the instructions to open, close, fetch, and so forth. A cursor can be explicitly declared and processed using a special loop structure called a cursor for loop. The open, fetch, and so forth is all accomplished automatically. We don't have to write instructions to perform those operations. We simply declare the cursor. And finally, if we use a select statement, we can use the bulk collect clause to retrieve a set of rows with a single select, and we'll put those rows into what's called a collection. There are 4 steps associated with the processing of an explicit cursor. Step 1, we declare the cursor in the declaration section of our program. We do this by using the keyword cursor and then giving a name to this work area, and following that with the SQL select statement that will be used to retrieve data from the database. Step 2, we open the cursor, which effectively causes the select statement to be executed. We use the open keyword and the name that we associated with the work area in the declaration of the cursor. Step 3, we retrieve rows through the cursor using the fetch statement. We follow the keyword fetch with the name of the cursor and then use the into clause to identify working storage variables that will be populated with the content of a row retrieved through the cursor. Now, steps 1 and 2 will be executed once for the cursor, but step 3 will be executed possibly many times. What happens is when we issue a fetch, we can think of this as a request for a row from the result set. And when you request something, your request is either granted and you're given a row, or your request is effectively rejected and say, well, I don't have a row to give you. So what this means is when we perform the fetch, we'll also have to follow this up with a test of the cursor attribute to see if the fetch successfully retrieved a row. The combination of the fetch and the test of the attribute would be executed potentially many times within the program. Hence, these instructions would be placed inside of a loop. And finally, when we're done processing the rows in the results set associated with our select statement, we close the cursor. This will free resources that were used to process that result set. We've mentioned that cursors have attributes associated with them. Here are the attributes that we'll see we can access for an explicit cursor. Percent not found, percent found, percent row count, percent is open. To examine a cursor attribute, we use the name that was given to the cursor in the cursor declaration and follow that with the attribute name. Now note that explicit cursor attributes can be used in procedural statements, that would be PLSQL statements, to control processing flow, but cannot be used in SQL statements. Now, any operation on a cursor that is closed, either not yet open or had been closed by invoking the close operation, raises an exception called invalid cursor. In order to determine whether a cursor is closed and avoid this possible exception, we can use the %IsOpen attribute and test the status of the cursor prior to making a reference to the found, not found, or row count attribute. Note that the isOpen evaluates to true if the cursor is open, otherwise it evaluates to false. %not found. This is also a Boolean. It returns a value of false if the last fetch returned a row. We had indicated that a fetch could be thought of as a request for a row. If we request a row, not found can be examined to determine whether or not that request was satisfied. So not found returns false if the last fetch returned a row, returns true if no rows were returned, and it is null before the first fetch has been issued against the cursor. %found, also a Boolean, evaluates to null before the first fetch against the cursor, evaluates to true if the last fetch returned a row, otherwise it's false. It evaluates to false if no row was returned. So notice that not found and found are essentially giving us the same type of information, just kind of holding it up to a mirror and seeing it one way or the other. And finally, the row count. This is an integer. It returns 0 when a cursor is first opened because no rows have been fetched into the program. It will be incremented after each successful fetch. So notice that row count can be thought of as a running accumulator or a running counter. After each fetch, row count is incremented if a row has been returned. So it's not until we've exhausted all of the rows in the result set that row count will reflect the total number of rows in that result set. So notice that reference to not found, found, and row count when the cursor is not yet open raises the invalid cursor exception. And again, we can use the is open to determine the status of that cursor. Here's a complete example. First, we declare the cursor and give it a name of C1. We associate that work area named C1 with the query that says select course number, name, description from course. Notice there's no where clause, so the assumption is many rows will be coming back. This will be all of the rows in a table, so it's not a singleton select. Furthermore, this select would be a type of query we could execute interactively with SQL Plus or SQL Developer. A set of rows would be returned and then rendered on the screen through that front-end tool. The open statement refers to the name of C1, issues the open, and effectively causes that select statement to be evaluated, and the result set is made available to us. Within the loop, repeatedly we issue a fetch against C1, which will retrieve one row, the current row that we're pointing to. We can think of the cursor as making the result set available to us as a sequential file. And the open will establish position at the first record, and the fetch will retrieve that first record or first row. The next fetch will advance and retrieve the next record, and the next fetch the next record, and so on. And we work our way through the result set as though it were a sequential file. Keeping that in mind, what we want to note is at some point when you read from a sequential file, you will have read the last record, and the next request to get a record says you're at end of file. There are no more records. How do we make that determination in SQL? Well, what we do is we use the %NotFound attribute associated with the cursor C1, and we say exit this loop or jump out of the loop when C1 %NotFound. Remember that that's an indication that no row was returned from the previously executed fetch. So that's how we'll terminate the processing. So notice that if a fetch is successful, not found is going to return false, and we execute the next instruction coded after the exit, which is simply to increment our counter of num courses, adding a value of 1, indicating another row has been fetched. Then we go back up and do another fetch, and so on. Finally, when we're all done, we issue the close, which frees up resources and changes the status of the cursor from open to close. So if we were to test is open, it will tell us it is now closed. Take a closer look at the fetch statement. Notice that the select statement associated with the cursor is selecting course number, course name, course description, 3-character columns. The fetch says fetch into, and we have 3 variables defined of the same data type. C number, C name, and C description. 3-character columns with the same data types as the columns CNO, CNAME, CDISC from the course table. That's the basic idea. What we'll do is go to the database, fire this up, and see what actually happens when we run this, and look at some variations of it. We didn't point it out, but the example we're using makes a call to the DBMS output package, specifically to putLine. In order for the data sent through putLine to be returned to the client and displayed on the screen, remember that we have to enable server output. And we've done that here, set server output on. Now we can take the code and run it and examine what happens. We get the acknowledgement message at the bottom, feedback message, saying that the procedure successfully completed. But just before that, we see this value of 14. The 14 was produced as a result of line 12, which adds 1 to num courses. Num courses was initialized in line 6 to a value of 0. So when we processed the first row, 0 plus 1, we processed 1 row. We processed the second row, going through the loop a second time. We add 1 to num courses, bringing it to 2, and so forth. Rather than present that total at the end, what we can do is effectively have a running total. We can show the effect of making a call to DBMS output putLine within the loop and executing this call once per row being processed, once per fetched row. So now we see a running accumulator, and we end up with a value of 14. That was the last time DBMS output putLine was called. When we go back into the loop, trying to process row 15, we do a fetch. There are no more rows, so not found evaluates to true. We exit the loop, skipping over lines 12 and 13. That's how the loop is terminated, and that's how we ended up with 14 as the resulting value. We have another way to do this. As an alternative to creating our own variable and using that with an assignment statement, adding 1, we can achieve the same result by using the cursor attribute %row count. Here we have included a call to DBMS output putLine, but instead of using num courses, we simply say C1 %row count. This works the same way as we just demonstrated using our own variable. Remember, I had mentioned in a discussion of row count as an attribute that it doesn't tell you the total number of rows within the cursor, but it tells you the number of rows that have been successfully fetched. And after fetching 1 row, the value is 1. After fetching 2 rows, the value is 2, and so forth. It's a cumulative count, a running total. Keep in mind that we're using the cursor attribute within a PLSQL statement. This is a call to DBMS output putLine. And we're doing this while the cursor is open. What would happen if we tried to make a reference to this cursor attribute for cursor C1 after the cursor has been closed? Let's take a look. Here we've made our same call as before on line 12, but we've included that call on line 15 after executing the close. Watch what happens. We get the same result, but when we try to execute line 15, what we see is it tells us the cursor that we're working with has been closed. It doesn't quite say that, but it's an invalid cursor exception that has been thrown. Remember, we said that any attempt to reference a cursor attribute other than isOpen when the cursor is closed will raise the invalid cursor exception. That's exactly what happened here. But an interesting thing to note, line 15 is where we made the call that attempted to reference cursor attribute row count for cursor C1, which has been closed. The error tells us the problem, an invalid cursor, is the name of the exception, and it also tells us that the problem occurred at line 15. So this can be useful in diagnosing problems. We'll take a look at one more example where we do something a little bit more productive than simply counting the rows. Suppose we wanted to actually work with the values that were retrieved from the fetch and use them in some way. Take a look at how we might do that. Remember, we're selecting the course number, course name, course description from the course table, and we're doing this for each row that we fetch. When we do the fetch, those values have been placed in, respectively, C number, C name, C description, our working storage variables. Here we've modified calls to DBMS output to say that we're going to be showing you the course number and name, and then we use C number, the variable into which we had placed C and O with a fetch. And we follow that up with C name, the variable into which we placed the course name when we did the fetch. Remember that DBMS output put and put line take a single argument, which is a character string. So in order to make this a little bit more presentable, we're showing the course number and a hyphen and then the course name. In order to accomplish that with simply two calls, we use the concatenation operator. So let's take a look at this in action. And there you have it. The examples we presented have focused on data retrieval, simply reading from the database. We'd like to mention also that PLSQL supports transaction processing. Assuming that we make changes to the content of the database, we need to signal successful completion of the transaction to the database, and this is accomplished using a commit statement. So commit marks the successful completion of a transaction, and this will cause any changes that were made during the transaction to be made permanent within the database and revealed or exposed to other users. Locks that were acquired to ensure concurrency control will be released when we do the commit. If we decide the changes should not be made permanent, we can cancel the changes using a rollback statement. The changes are undone and locks are released. We return the database content to the state when the transaction began. Now we shift our attention to stored PLSQL program objects. A PLSQL program can be defined as a procedure or function and then stored in the database. The examples we've given thus far have been what we refer to as anonymous PLSQL blocks. They do not have a name, so they are not stored and cannot be invoked or called. But when we create a function or procedure as a database object, these objects are stored within a database. They're given a name, which means we can invoke them by calling them using that name. There's a specific data definition statement for each of these types of objects. We have a create procedure statement and we have a create function statement. Just like other database objects that are created, these PLSQL program objects would have metadata recorded about them in the system catalog. A stored procedure or function can be created as an independent or standalone database object. They could also be bundled together in what's called a package. Because we're doing a very quick presentation of PLSQL, we're going to focus simply on a simple standalone stored procedure and standalone stored function. To create a stored procedure, we use the create procedure statement. The body, the executable code, is written in PLSQL. Oracle Database allows stored procedures to be written in other languages, but our current interest lies with PLSQL, so that's what we'll examine here. When this statement is run, the procedure is compiled. the source code and this compiled or object code will both be stored in the system catalog. As we examine the syntax for the create procedure statement, we see several locations where there are square brackets. Recall that these square brackets in our syntax diagram indicate optional components. So we could begin by simply saying create procedure, give it a name, and so on. We alternatively could say create or replace procedure, in which case if the procedure does not exist, it will be created. If the procedure does exist, it will be replaced by the definition we're providing at this time. Notice that parameters, which we've denoted here as parm, are also optional. We'll have more to say about those in a moment. So a procedure could have no parameters or could have several parameters. Then we can use either the word is or the word as. There's no difference. It's just a matter of preference. And then we declare local variables and subroutines, whatever is necessary. We have the executable section, and optionally, we can have exception handlers. And finally, the last part, which is a nice thing to do, but not required, is to include the procedure name. We'll place the procedure name after the create procedure keywords, and optionally, we can use that same procedure name after the word end. It gives a visual aid for the boundaries or delimiting the body of the procedure. After we've created the stored procedure, we can call or invoke a stored procedure using interactive tools such as SQL Plus or SQL Developer. This would be done using the execute command, which can be abbreviated as exec. The syntax for this command would be the keyword execute followed by the name that had been given to the procedure in the create procedure statement, and if the procedure has parameters, a parenthesized list of parameters. The parameters that we provide when we execute the procedure are referred to as actual parameters. The list of parameters specified in the create procedure statement would be referred to as formal parameters. Generally, the parameter list on executing or calling the procedure would have a one-to-one correspondence. We would have one actual parameter for each formal parameter. The exception might be if we have parameters that have default values. We can talk more about this in a moment because there are two ways to supply parameters when we invoke a stored procedure. We can use kind of an ordered list, or what we can do is use a name and associate that name with the actual parameter. Now, the procedure name that we specify is the name that was associated with the procedure in the create procedure statement. The parameter list would be a list of variables or possibly values. We'll talk about that when we talk about parameter mode in just a moment. Now, a stored procedure can also be called from within a PLSQL block using only the name of the procedure. There's no need for an execute statement. The syntax here would simply be the procedure name followed by the list of parameters within parentheses, assuming that the procedure had formal parameters. Here is our first example of a simple standalone procedure. And this is being specified in the schema of the current user. We're not sharing it with other users. So the procedure has no parameters. We say create procedure, we assign the name total, and then we immediately go to the word as to introduce local identifiers. What this procedure does is counts the number of rows currently present in the course table. Because this is not interactive SQL, we have to provide some work area to store that value, the number of rows, the output of the count function. So we create a variable called quantity, which is numeric, and we take the result of the count function and store it in this local variable called quantity. To communicate back to the user, this simple application makes a call to DBMS output put line and displays the value of quantity on the user's terminal. This is not the best way to write a stored procedure, but we're trying to ease you into the process of getting acclimated with how stored procedures operate. Let's take a look at this on the system. Note on line 10, we have that slash, which signals the end of the input stream to the front end tool, which then transmits the entire create procedure statement to the server for execution. In executing the code, it will compile it and store metadata and the source code and the compiled form of the procedure on the server. It will not execute the code. Remember that we need to have server output enabled if we're going to be using DBMS output. So we'll say set server output on, and now we're ready to invoke the stored procedure. We can do this simply by saying execute followed by the name of the procedure because there are no parameters to be supplied. And we execute this, and the result of server output being on and the DBMS output put line call shows us 14, the current number of rows in the course table. We also could write an anonymous PLSQL block. Because we don't really need any work areas within the block or the program that calls the stored procedure, we can simply go right to the begin keyword, the executable section. And this is what we might use for code. Simply within the executable portion of the anonymous block, put the name of the procedure and then the semicolon to signal the call. Again, this is a very simple procedure. There are no parameters. So when we proceed to execute this, we get the same result. Again, we get 14. The call to DBMS output put line was not made within this anonymous block, but was made once again within the stored procedure. This is not the best way to write the stored procedure if we want it to be generalized and be able to communicate with it, passing data to it and receiving data back from it. We'll talk about that in our next example. When we define subprograms in PLSQL, we indicate how we're going to communicate with these subprograms, how we'll pass information into the subprogram, and how we expect to get information back from the subprogram. So this is accomplished by specifying the parameters or the arguments and specifically indicating what is referred to as the parameter mode of the parameter. So each parameter must have a parameter mode. There are three possible settings for the parameter mode. In is the default. If we're silent and do not specify a parameter mode, in is what will be used. In allows us to pass a value in one direction into the subprogram. So the actual parameter that we provide could be a constant value, could be a literal, could be a variable that has been initialized, or could be an expression that will be evaluated to obtain the value. Out as a parameter mode requires that we use a variable. This is because out goes in the opposite direction. This is a way for the subprogram to return a value to the invoker. So there will be assigning a value, therefore this must be a variable. In-out provides a two-way street. We're going to pass some initial value into the subprogram, and through the same mechanism, the subprogram will return a value to us. It'll be an updated value. So therefore, this also must be specified as an actual parameter using a variable. Here's an example that involves two arguments. The first argument, department or DEPT, is in mode. We were silent as to what the mode is, so it defaults to in. Notice the second one, we specify amount. Its data type is number, and what we see is this is an out mode. So when we call summarize, the name of this procedure, we can pass a character string as a literal or as a variable for input, and we'll have to give some variable to receive the number that is returned through amount. We create a local variable called quantity, which is of type number. We again count the number of rows from the course table, place that count into the local variable of quantity, and what we do is we return that value not by using DBMS output, but by assigning the value to the out mode parameter. Additionally, the input parameter, department, is used to complete the predicate in the where clause, indicating which department's rows we will be counting. So rather than counting all of the rows in the course table, we're going to count the rows for a particular department, the department specified by the input parameter. Take a look at this on the system. In this syntax, instead of simply using the create procedure statement, we specified the or replace option. If summarize did not yet exist, this would be its initial definition. But if summarize already existed as a stored procedure, we'll overlay that existing definition with the one we're providing here. When we submit the code, again, we simply get an acknowledgement that it was created, which means the code was successfully compiled. Metadata about the procedure is stored. The procedure source code is stored, and also the compiled version of the procedure is stored in the system. Now, in order to run this procedure, we could use an anonymous PLSQL block. Take a look at this code. Here, we're declaring two work areas. How many is declared as a numeric variable? Which one is declared as a character variable? When we call summarize, the first call on line 8 passes the department of CIS as a constant or literal value. That's fine because that will map to the department input parameter. The second parameter, because it was out mode, has to be specified as a variable of type number, so we use our local variable here of how many. When the procedure call completes, control will return to line 9 of this program, and we make a reference to the value that got placed into how many within the procedure. The second call on line 13 uses the variable called which one to show that the in-mode parameter can also be an initialized variable. So in that call, we'll get the result of how many rows there are in the philosophy department. We get 6 and 4. 6 would be the number of CIS rows. 4 is the number of philosophy rows. So those are two examples here for calling this stored procedure. We had mentioned that there were two ways to pass parameters into a stored procedure. One is a positional notation. That's what we've demonstrated with this program. We've passed the first actual parameter mapping to the first formal parameter, the second actual parameter mapping to the second formal parameter. As an alternative, we can use what is called named notation. With named notation, we put the name of the formal parameter and then this equal and greater than combination, which is referred to as the association operator, and then the actual parameter that we will associate with the particular formal parameter. So what we're doing in this example is associating CIS with the input parameter named department and associating this local variable how many with the output parameter called amount. And when we run this, we get the value of 6 because there are 6 rows in the CIS department. This may raise the question of how do we know what the names of the formal parameters are, especially if we didn't create the stored procedure? What we can do is we can use a SQL+ command called describe. And we can describe the structure of a table with the describe command. But what we're looking at now is stored program objects. It turns out that describe works with these as well. So the name of the routine we're calling is summarize. We'll describe summarize. And when we describe this, it tells us that it is a procedure and it has two arguments. One argument is called department and the other is called amount. It tells us the data types of these arguments and also tells us the parameter mode. Department is in, amount is out. Furthermore, if the parameter has a default value, it tells us that there is such a value. So describe actually generates a query sent to the database to examine the metadata for a stored program object. Here we're using it for a procedure. In just a bit, we'll take a look at declaring a function and using describe there as well. A stored function is another type of program object. On the surface, it looks very much like a stored procedure. We have a create statement, which includes local declarations, executable instructions, and optional exception handlers. But the difference lies in how we communicate with a function. A function always returns a single value. To accommodate this requirement, we see the return clause in the create function statement. This announces the data type that will be returned for that single value. We'll also see that calling a function is different than calling a procedure because we must accept and consume that value in some way. Here's an example of a standalone function, again stored within the schema of the current user. We're not addressing issues of sharing access to this with other users. This is a very simple function in that it has no parameters or no arguments. Again, we say create or replace function, meaning that if the function does not yet exist in the system, it will be created. If it does exist, it will be replaced by this current definition. The name of the function is course count. Again, there are no arguments or parameters. If we had those would follow the name of the function and precede the return clause. The return clause here indicates that this function, when it completes execution, will return an integer to the caller. We then have a local variable called quantity, which is of type number. We count the number of rows from the course table, placing that count into the local variable of quantity. We then use the return statement to push that value back to the caller. So notice that we're returning quantity, which is of type number. We had announced we would be returning an integer. Number and integer are compatible, so that works fine. Let's go to the system and give this a try. Okay, we've run the create function statement. The function has now been added to the system. We're ready to try to run it. Remember that we can run it interactively from SQL Plus or SQL Developer by using the execute command. But because the function returns a value, we have to accept or consume that value in some way. What we're doing in this particular example is invoking DBMS output put line, which makes a call to course count. The value returned by the function course count then becomes the argument to put line and will be displayed on our screen. And here we have 14. Note that we could have modified this slightly. In many languages, when you have a function, the function, even if there are no arguments, requires parentheses. Here, the parentheses were optional. We could also invoke course count by using the parentheses, making it clearer that we're invoking a function, even though we don't have an argument. Let's look at one more way to invoke this. We had mentioned PLSQL code could make a call to the function. Here we have an anonymous block where we're making a call to course count. And again, we could do this using parentheses or without the parentheses. Course count will return the value, storing it locally in the variable how many, and then we'll display how many by making a call to DBMS output put line from within the synonymous block. And again, we get a similar result. In our final example, we create a variation on our previous example. Here we call it course count 1. The primary difference is that this particular version of course count 1 has an argument. It has a character string as an argument. That character string will be used to identify the department whose course rows will be counted. But we also want to make this have a default value, so the argument becomes optional. If the department is not passed, we assume the value of null. We test that with an if statement. So if the value of the argument is null, then we count the number of rows in the course table independent of any department. However, if a value was passed, we use that value to complete the predicate in our where clause and identify only those courses where the department is equal to the value that was passed, and we count those rows. But in either case, we return the count, which is placed into a variable called quantity. Let's look at this in action. Okay, we've created the function. Now let's give it a try. Here we have an anonymous block where we again have a local variable, which is numeric, called how many. We have a character string variable called which one, which is initialized to philosophy. The argument to the function can be a literal, and we're using CIS in the first call on line 8. Then we report the number of courses sponsored by CIS. That argument could also be a variable initialized to an appropriate value, and we're using the variable which one, which would identify the philosophy courses. But remember, because this function has a default value for its argument, we could also omit passing an argument. And on our final call on line 20, we're calling course count 1 and not passing it any argument. This will count all of the rows in the course table. So we see that there are 6 CIS-sponsored courses, 4 courses sponsored by philosophy, and the total of all courses independent of the department is 14, and we use that default value. Now let's take a closer look at the describe command that we discussed earlier. Let's describe course count 1. Here it's showing us that this is a function and it returns a number. The argument that it has is called department. It's a character string. It is an in-mode argument, and it has a default value. Remember that we had created course count, and that was a function, but it had no argument. When we describe this, it simply tells us it's a function that returns a number. It doesn't tell us that there's no argument, but the absence of that additional information is what tips us off. Let's look at one more point. We have created a couple of functions and procedures, and we defined the parameters and the arguments. But the data types we use require a little bit more of an explanation. These data types are specified as unbounded. Notice that the department argument for course count 1 was specified simply as char when we created the function. And furthermore, it's listed here simply as char. There's no size. If we go back and look at that code, notice it simply says char. It doesn't say char length of 4, just says char. So when we specify the data type for an argument or parameter, we don't constrain it. It's unbounded. The same would be true for numeric data. We don't specify a precision and scale. We simply say number. So that allows us to provide any value that's necessary. But keep in mind that it's unconstrained. If we were to define the parameter or the argument in the create statement as having a particular size, we'll get an error. Let me just show you what that looks like real quick. Let me grab this code. We'll make a quick little change. And let's suppose we had said this was char length of 4. Remember, this is create or replace, so this will alter the definition that's stored in the database. So now we try to run this, and it says it was created with compilation errors. We know that this code worked fine just a moment ago. The only difference is constraining the size of the argument. So how do we find out what the errors are? Well, SQL Plus has a command called show, where we can say show errors, and it will reveal to us the errors that resulted from the most immediate compilation. And it tells us that it encountered the symbol of a left parenthesis when expecting something else. So what we see is this is line 2, column 14, which is right here. Again, this is the response of the system when we try to constrain the size of the parameter or the argument. A very nice feature of PLSQL is the ability to have the system assign the actual data type for a variable rather than explicitly code this data type. This is based on the fact that PL/SQL variables and constants have attributes such as data type and structure. Database tables and the columns within these tables also have attributes. We can code %type to specify that we wish to inherit the attributes of something else. For example, we can specify some identifier that looks like a particular column of a particular table by specifying the table name dot the column name %type. So rather than hard code varchar2 length of 20, we're saying let's model it after the CNAME column of the course table, and we say to do this by specifying the %type. Then this variable will have the same data type and size as this column. This makes it ideal when we select into this variable. So if we're retrieving a value from the CNAME column of the course table, we don't have to hard code whatever its data type and size is. We can actually have the system look that up as part of an inspection of the metadata and then create our variable with the same attributes. This is really nice when we have to do maintenance of code, because if we change the attributes in the database, the code simply needs to be recompiled and it will pick up these changes. There's no need to modify an actual instruction and say, oh, we changed this from size 20 to size 25, and we have to change the 20 to 25 within the code. So it's a pretty nice feature to be aware of. So what have we discussed in this video? We've discussed embedded SQL and the use of an explicit cursor. We defined the 4 steps associated with using an explicit cursor. We then discussed attributes for cursors. And we specified how these could be used in controlling the processing of the cursor. We introduced stored procedures, discussed the syntax for declaring a stored procedure, and discussed the syntax for invoking a stored procedure. We did the same thing with stored functions. And finally, we discussed attributes for variables.